Alright, so in this video I'll show you how to get started with the Silent Hill Decompilation project. And I assume you know C and you know how to build this game. You downloaded the repo, you compiled it, and you just want to get started. Or you're just curious and you wanna have a look at how this process looks like, then feel free to watch the video. So again, you've downloaded the source code, you compiled it, now you just want to get started. So let's pick some C file, let's say map1s01.c, and this is the first floor of the school level. Because in this game, every level is split into individual binaries. So some of the code is repeated, some code is unique, and we have separate, C files for each. So if you open such a C file, you'll see a bunch of C code, obviously, but there is also those include awesome directives, which means that those are the not yet decompiled functions. Instead, we take the disassembled assembly from the game, right? So during the build process, the whole game will be disassembled. Each function will be separated into an individual file. And then if we don't have the C code yet, we just take that file and link that in, right? And the goal is to replace all those assembly files with C code. So once you pick your function, you can just search for it by the name. Just keep in mind that some names can repeat in different binaries because the name is just func underscore the address. So as you can see, we have the same function name in map1s00 and map1s01, but it's not the same, right? So make sure you pick the correct one. So as you can see, that's the assembly code of this function. So what do you do? Well, you go to decomp.me/new and create a new scratch. Now you have to create your account here, or rather link your GitHub account. Once you do that, you'll get your profile, you'll have your links here and so on, your projects. It will remember that. So you go to this page, you select PlayStation, you select Silent Hill, and the compiler, everything will be filled out automatically if you just select the preset Silent Hill. So now just copy this assembly, paste it into the target assembly. And for the context, I already have some context because this website will remember the last context you used. But for the first time, you'll have none. So you have to generate it. And for that, there is a tool in the repo called m2ctx.py. And you give it the C file in which that function is used. And this will generate the ctx.c file, which is basically all the function declarations and structures and enums and all the macros, right? Dumped into a file. So you put that context in and you create a scratch. And this scratch, as you can see, you get a unique link, and this link you can share with people. Other people can join in and help you out with this function. So, that's a collaborative process on this website, right? Okay, so as you can see, the decompiler used on this website already gave us some code, and it looks kind of messy, but there is some structure to it. We can see some function names and so on, so it's not completely nonsensical, but it doesn't compile yet. And on the right here at the bottom, you have a window with all the warnings and errors, but even without looking at that, we can already see a problem. Those question marks here, that just means that the decompiler failed to recognize the type. So what do you do in such a case? Well, you either have to try to deduce it or guess it, right? And honestly, a very good guess is usually just S32, which is the int, right? Integer, because that's the most common type in C. And since this is a 32-bit platform, a pointer will also match S32. So that's a usually very good first guess, and it's usually correct, right? But just to make sure, let's see how this function is used. I see it's used here in two places. It seems it doesn't return anything, and it just takes 0 and 1, so it could be an int or maybe a boolean. So let's just put it as void doesn't return anything and S32. So that problem is solved. Second problem is this type, it doesn't know what it is. We can see it's used as a some object, some structure with fields at those offsets. Those are like generated automatically. So at offset 1C, we assign this number. At offset 20, we assign this number, and so on. So usually for such a case, you would actually create new structure and try to match those fields, right? And as time goes on, maybe another function uses this object, uses another bunch of fields, and whatever is written to them or however they are read gives you some kind of clues what it is actually, right? And you can kind of deduct and then name that field accordingly as, I don't know, position, rotation, or health points, stuff like that. But for this, actually, we don't have to do that because notice that this object is named, unlike the one above, which is just the underscore and the address, which is something we get automatically for unknown types yet, or rather, it knows it's an int, but it doesn't have a name. But this one has a name, but it doesn't have a type, which is strange. So let's search for it in our repo, and indeed, I see it is declared as world object desk. So this should be the part of the context, but for some reason it wasn't. It might be a limitation of the context generation tool or some problem in our repository, in our setup. But, as a workaround for now, let's just paste that line to the context at the bottom. And if you press decompile, you will get the decompilation again. And as you can see, right away, it actually filled out that information and we set up this position and rotation. So this shows you how the context works, where as you update it, as you put more informations, the initial decompilation gets more correct, more filled out. And so we can also take this function, this declaration of a function, and let's declare it as void and taking s32. So that goes away. And now the second or third problem with the question mark is that this function apparently is taking some argument, but of an unknown type. And if we look how it's used, it's like, okay, we assign arg to var a1, and then var a1 is like passed here. So, I mean, that is kind of possible, but why shouldn't be like direct, right? So it seems kind of sus, let's say. It doesn't seem right. So this might be another decompilation limitation where it's a false positive, let's say. It doesn't take any arguments. And unfortunately, in MIPS architecture, which is the CPU architecture PlayStation 1 uses, it's not always obvious whether a function takes an argument or not. So the compiler obviously tries its best to tell, but sometimes it fails. Okay, so let's copy this new decompile code into our source code tab. And it still doesn't work, so let's try to figure out what's wrong. So there is a bunch of warnings which you can ignore for the moment, but let's focus just on the errors. So the error is too many arguments at line 42. Let's see. Okay. So let's grep for this function. And indeed, I see it doesn't take any arguments, so this is some garbage. Oh, and right away we actually compile and notice that look how much code is already matching. It's like 78%, which is not. It's kind of random whether you'll get a nice decompilation right away. Sometimes you might get like 1%, and there will be a lot of fix-up required. But this is kind of easy function, let's say. It doesn't have any wild compiler optimization nonsense that makes it hard to decompile. Okay, so now let's try to fix each issue as they appear. So the white code on black means it matches, there's no diff. Now those colors means that, for example, here we have some additional code which is not in the original, and vice versa, right? In the red it means that in the original there is some code, but we don't have it. In this case, we can see it is actually the same piece of code, but it's misplaced. Here, for example, the jump label is different, which means like we have the same code, but at the end we jump to a different place, so the flow logic is a bit different. And blue just means that in the same spot we have completely two different instructions, right? So there is some kind of conflict. Okay, so let's move. For now, we can remove that because that usually means we use more local variables. So allocate, two more on the stack. That will go away on its own once we clean up other stuff, usually. All right, so first thing that we want to fix up probably is those go-tos. Why they happen is if we have the same code repeating over in a function, the compiler will do an optimization pass where it will remove those duplicates and just issue a goto. But if you write those gotos that way yourself manually, the code is actually generated a bit differently. So you have to kind of undo this optimization. So actually, let's do that. So you can see we have a block 12 here, which calls a function, then it just returns, and we have a goto here. So most likely it looked like this, and boom, that actually fixed that conflict there, and now it matches. So let's do the same for other blocks. We have a block 25 here, which is here. And do we have any other gotos? Let's see. No more gotos. So we can remove those labels now. And notice that both cases basically call the same function, but with different arguments. So what the compiler did is put the arguments into variables and then call a function with the variable. But now we could actually like inline those arguments, and this is actually the most likely way, how it was written actually. Right, like so. And we can do that at the end, because for now it doesn't actually affect our matching. Okay, so but it might. It's not always. Sometimes it actually affects whether you use arguments directly or through some temporary variable. Sometimes it makes difference. Okay, let's see. Here I see a difference because a number is positive instead of a negative. Where is it? And by the way, when you click on a line in C, it will highlight the part of assembly. Actually, let me make the window larger. So that way you can kind of see where each issue is. Okay, it is here. Okay. Okay, we'll come back to this a bit later, because I feel the other issue I see right now we might actually affect it. So here's a very common pattern in this game. This entire game is not using any floats, it's using fixed point math. And actually all those big hex numbers are mostly small numbers, but they're represented in this fixed math. And I'll show you how to convert them a bit later. But this line is kind of problematic. If you look at it, it does like a very strange math, right? It's like shift by hex C, then OR it with this, which is divided by some weird number, shift 14, like what the hell, right? Well, this is just how the compiler optimizes 64-bit multiplication. Since this is a 32-bit system, it actually has to do it in chunks, and I guess the compiler kind of did this wild math, which is equal to just doing the 64-bit math. So and we have a macro for 64-bit multiplication, and this will appear a lot. So it's like a clear sign. If you see like a shift by C, then shift by 14, and this or something like that, and here is another case, and this mult high as well, and here, that's a clear sign that 64-bit multiplication is taking place here. So, and by the way, I see that this temporary V0 is equal to all this math plus this rotation C Vx, and we then assign it to rotation Vx. So actually we can probably write it like so. We just add to this rotation Vx, and this is the macro I was talking about, multiply precise G delta times 0, this argument here, and third argument is Q12 shift, and I'll explain later why that is. That's part of this fixed math, and that's a topic on its own, so I'll come back to this. Okay, we can remove this. Now, We used to have this value in the temporary temp v0, so now let's replace it with this. And now it matches. Some registers are different, but this either will go away once we match more code, or we'll have to come back to it and kind of play with this code more. But at least logically, it appears to do exactly the same. So for now, we can leave it. Now, here's the second part, which does this 64-bit math. Let's try to decode this. So we have some temporary variable, which is equal to this global plus g delta time 2. Then we multiply g delta time with this value, okay. And then we assign this to this. Okay, so I'm gonna comment this entire block for now. And let's try to rewrite it like so we added this g delta time 2. And then let's say for the time being, we will take this variable, or actually, I'm gonna just declare a new one. I'm gonna declare my own temp0, temp1. And by the way, those ones will clean up at the end. For now, let's just leave them. So I'm gonna use temp0, which is equal to this fp multiply precise. And the precise, by the way, the precise is what makes this, it's 64-bit, right? It's gonna do like 64-bit inside this macro. G delta times 0, and this timer, or this global, whatever it is. But I guess it is some timer, we add time to it. Okay, and what's next? Okay. To this value, to this rotation, we add multiply precise g delta times 0 times c00. It will shift. Oh, yeah, here. Like so. And now for position Vy, I think we add this, whatever we calculated temp0, because I see it like this: temp low, temp high. Temp low, temp high is part of this g delta times 0 times this other counter. So I think that's correct. And for Vz, we do also an addition, multiply precise g delta times 0 minus hex 8000 q12 shift. And let's see if that matches. I mean, it looks more correct, but not quite. So there is some mistake. Oh yeah, because this part is also unfinished. Okay, so position Vy. So how is temp? Okay, okay. Yes, yes. Okay, so like so. Okay, now I guess that part is fine. This return is not needed here anymore. Let's look at this again. Okay, it's possible that this is actually done inline like so. Oh yeah, okay, good. So see, this is a clear example of we have code that would do exactly the same thing, right? If we compile this function, put it into a game, there will be no bug. We do the same calculation, but in slightly different order or in slightly different way, and it produces a complete different match. So this is the kind of stuff you actually have to do when you do matching compilation, where you kind of spend more effort on, tweaking the code to make it match exactly. But on the other hand, you have the guarantee that the code is correct, because if it's the same, then it's the same. There's no possible of introducing new bugs, right? Okay, let's scroll down. We are at 99.92. So where is any mismatch? Okay, it's around these numbers. Let's see what's wrong here. Okay, so now I'm just using a kind of deduction, or let's say pattern matching. Like I recall in this code they like to use or when I assign values to position vectors, they usually do it in an order where it's first x, then z, and then y at the end. And here is z first. So let's see if just swapping them around makes any difference. And indeed it does. Nice. And here I guess I forgot a minus. Yes, and now we're matching. So we're done. This function is actually matching. So technically you could just move it into the repo and it should build and everything should match. But before we do that, let's try to clean it up a bit. So let's talk about these numbers. Like I said, this game is using fixed math, which means you take an integer, you split it, and part of that integer is for the whole number and another part of it is for the fractional part. And there are different formats where you have more or less precision, right? The most commonly used format here is called Q19.12, which means you have 1 bit for a sign, 19 bits for the whole number, and 12 bits for the fractional part. And this is why you do this Q12 shift, which means shift the number by 12 to the left, which will move the whole number to the left, right, and what's left on the right, let's say, is the fractional bits. More or less, there are different formats. For example, angles use different format, positions use different formats, and so on. It's kind of hard to wrap your head around, but you'll get used to it. Let's say you just have to, I, for example, never used those numbers before joining here, and now I kind of, you just get it, right? So obviously you don't have to do this conversion by hand. We have a bunch of scripts for that. For example, I have a script here which will just convert this and actually, put it into my clipboard right away, so I can just copy and paste it like so. And see, so this seemingly large number suddenly just becomes minus 112 in floats, which looks much more sensible, and it still matches, right? So that you can tell it's exactly the same value. So let's do it like this. Now this well, in this case, it still matches, but you can see it's like 7998, and actually, if I put just comma 8, it still matches. And this actually shows you the limitation of the precision, right? Where 7998 is not equal to just dot 8, but the precision is low enough where those two numbers are actually equal. But old system, old game, and so on. Okay, so here for 0, we can just put 0 like so. And this we can do like so. Oh, and in this example, for example, my script says, oh, this number is equal to 27998, but if I put it to .8, it actually matches. So it's like off by a fraction. My script is not as, it doesn't do it precise enough, let's say. Actually, it's a minus, it's a negative number. If I double click on it, it doesn't highlight the minus. Unfortunately, I have to add it manually. Yeah, same issue here, .8. I'll probably have to work on my script to get rid of that because it's annoying to do it manually. Okay, so that's what you would do for those kind of numbers. Now, not every number is gonna be fixed number, right? But if you can see like, okay, it's involving math, positions, rotations, timers, then it's in that format. Okay, so let's try inlining those arguments. So this is gonna be false, 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 and this is going to be 1b, which is, 1b in hex is 27, and I'm going to talk about this in a bit. This is gonna be 29. Yeah, and this is true. This is 5, and this is 19, yes? No, how much is 15 hex? 21, sorry. Okay, so we can remove that. Now, this is a function that will display, the subtitles and like in a cutscene, right? So we can actually look at the list of the messages in each map and figure out which message it is. So the first common is always gonna be all maps have the same 50 messages, and those are for the common stuff like you found ammo, you found a knife, you found something, right? Those common messages, and then you have all the unique ones. So for 27, it should be um, like 12 from here, and it says there is some blood on some of the keys. So we're gonna leave a comment. There's some blood on some of the keys. So we can already tell that this is the part where you interact with the piano, right? And 29 is two more. Check the piano. Okay, check the piano. Now notice that here is false false, which means it's like a message with no selection, but this actually is a message which does a selection, and this means what to do when you select yes, and this is what to do when you select no. And this is about those cases here. So in state 4, so when you select 5, you go to state 5, and when you select 21, or sorry, when you select no, you go to state 21, which is here. So we can actually make a nice define for it, like define state check piano, which is 5, state don't check piano 21, right? And let's replace it like so. Okay. Now, another pattern which I see, and I am surprised I didn't mention it before. I guess I kind of forgot because it started compiling so early. But this piece of code, notice that it repeats all the time. It's here, it's here, it's here, it's here. So you'd think, okay, let me put that into a macro or inline function so I don't have to copy paste this code all over the place, right? Well, we already did that because this is a common type of a function. It's like an event function that drives cutscenes and interactions with objects, and all of them follow this kind of structure. So we already have a function called syswork state step increment. So let me just copy that and replace it. And notice I'm going to replace this and it still matches, right? So it's correct. So let's put it everywhere. And here the last state is like, leave the cutscene, go back to gameplay, which we also have a function for. You can tell because it's assigned a sysstate gameplay to sysstate, like so. That's the argument. And this is, all of those were increment states. So if you're in 8, go to 9. If you're 9, go to 10, and so on. And this is like, go to a specific state, which also, we have it here, for example. But the argument is -1 here instead of 8. So, and -1 is not defined, so it will jump to the default case. That's the logic here. And actually, you can replace it with no value, which we define as -1. It also appears in a lot of the code. Okay. Also at the top, we have a sort of common pattern where this logic is like, if you press a button, then skip forward, right? Usually in cutscene events, it's like, if you press a button, then just jump to the end, and that's how you skip a cutscene. So let's look for it. Skip for, here I have example of such a case. But here, usually we check like if you're in a state between X and Y. Here it seems like we only check if we are above A0. So all the first stuff here must happen. You cannot skip it. But we can still, let's say, copy this part of the code. Let me think. Yes, so it's gonna look something like this. And now we remove this part, and it was supposed to be greater or larger than hex 10, or I can look at the compilation again. So it was 8, which is 10 in decimal. Okay. Okay, and I see it still compiles, it still matches. And now 13 is 19. So if you're less than 19, then do a screen fade and switch the state to hex 11. So again, I'm gonna copy this function which changes a state. Where is it? We have somewhere at the bottom here, right? Yeah, this. This part is gonna be 11. Or sorry, it was hex 11, right? So 17. Okay. So if we press a key and we're less in state 19, then jump to state 17, which is here. So this is like skip piano, state skip piano, let's say. And we can define it. And what's the significance of that of the wait. This argument, wait, this is not used. Let's see if I comment this out. Does it break anything? No, it doesn't. So see, this was like some, I don't know, some decompilator artifact, let's say. And actually, so this matches our macro here, where we check like, is it more than this but less than that? You see, it's like as two separate ifs, so we can actually do it like so, and remove this brace and this brace, and move this. Yep, and it still matches. So this is nice because we follow the same pattern as other functions, right? The more it repeats, the better. Okay, and for the screen fade, we also have a macro for it somewhere, bodyproc.h. This is like reset timestamp, I believe. G screen fade. Maybe it's in game.h. No, where is it? G screen fade status. No, it is in game H. 154. Yeah, reset timestamp, that's equal to this. Now, you would not know this automatically, and actually you just leaving it like that would be fine, but I happen to know this, so I'm gonna replace it and just make it a bit nicer. Same here, we can make it like so, this is equal, right? But it just makes it more clear that we are setting the first flag in this field of flags. This we can remove. So anyway, you basically you get the idea. You would inline those, you would convert those numbers to this Q12 notation, and so on and so on. So, and yeah, we can actually, I think we can already remove those. Oh, not yet, it still errors out, but it's probably just because I'm using those. So let's do it quickly. Yeah, and now it's all gone. And actually those two also can be removed. Yeah. So now I'm gonna show you how to like move it to the repo, right? So we have it completed. So let's open our file, this map1s01, search for this function name, and here it is. So we remove this include asm and paste our source code. So, congratulations, you just decompiled your assembly into C, right? And that's how it looks like. Those externals that appear here, you should put them into their own header. As you can see, we have a bunch of them, like so. And you can scroll down. I see, oh, there is a warning that this function is not declared. Oh yeah, because this is this function that we just declared, and this is the function we just decompiled, which is also nice to put declaration of it into the header. And this is the function that we actually call, but is also not decompiled. And right now we don't know anything about it, but through the compilation of this function, we uh, at least assume, at least we have a strong guess that it doesn't return anything and takes S32 as a type. So let's also put this into the header declaration of them. So now this warning disappears, and let's build it and let's see if it still matches. Okay, so we built it and everything still matches, so it's good. So what do you do now? Well, just make a commit. You can name it anything you want, but at least we usually just put the name of the binary and the function name and like so. And you have a commit which you can submit to our PR. Make a PR on the repo and it's gonna be merged. So I hope you learned something and was interested. And if you wanna give it a shot, trust me, it's pretty fun. It's a nice hobby to have. So give it a shot. All right, see ya.